Hello everyone, welcome back to another discussion in dynamics. Today we will start a new topic, namely we will start kinematics of rigid bodies, and our subtopic will be rotation about fixed axis. Plan for today is following. We will start with a brief lecture review, and then we will do 3 examples, 1, 2 and 3. Alright, without further ado, let's begin. Let's dive straight into our discussion. Let us start with a brief lecture review. So, let us assume that we have a rigid body of an arbitrary shape. Let's say such shape. This is rigid body. Let's also assume that our body is fixed at this point. Let's call it point A. And let's also say that we know velocity of this point. Let's call it point B. Velocity of this point is, of course, perpendicular to that line. It has to be. Additionally, we know this distance. Let's call it distance d. Okay. In order to figure out what is omega of the body, so angular velocity of the body, we must know what is the magnitude of this VB. So let's assume that VB is known. In that case, we can find omega b using a very simple equation. Omega, or actually, I prefer to write it in this way. VB is equal to omega body times d. And from here, we can see that our omega body is VB divided by d. Please observe that this is a scalar equation. We will use it today a couple of times. And I believe that also once we will use a more general equation. Namely, v of some point j can be expressed as v of some point I plus omega body times r j relative to I. This expression tells us what is the dependency on velocities at different points of one rigid body. All right, that's all I would like to say about the brief lecture review. Now let's do example number 1. Feel free to pause the video and familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? We have our turbine, and they told us that it is rotating clockwise, right? And they also told us that this distance is r, and r is 182 feet. Additionally, we know velocity of this point. Please observe that there is 90 degrees between the blade and this velocity. They ask us to find the velocity of this point, of point B. So let's do it. First of all, I would like to find omega of the turbine. Let's say omega t, just for clarity. Let's use our equation from the previous board. I believe that our omega t, or actually velocity A, is equal to omega t times r. From here, we can see that omega of turbine is equal to VA divided by r. Let's plug in values. Let's grab calculators, and then we will see that omega of the turbine is equal to approximately 1.604 radians per second. Great. Now, once we have omega t, we can find velocity of B. So velocity B will be again omega of the turbine times this distance times r divided by 2. So this will be approximately 1.604 times 292 divided by 2. Grab your calculators and obtain that this is approximately 146 feet per second. The question is, what is so this is magnitude of VB. Now the question is, what is VB vector-wise? I think that based on the picture, we can clearly see that VB will be pointing this way. So our VB is exactly 146 J feet per second, or if you prefer the other notation, you can write VB is equal to 0.1460 feet per second. This is the answer. And this is the end. This is the end of problem number 1. Now let's do example number 2. Again, feel free to pause the video and read and understand the problem statement. All right, so what do we have in here? We have a pulley structure presented in this picture. Not a picture, a drawing. And we know that this point, point B, has following velocity and acceleration. Moreover, we know that the diameter of this pulley is L, and that the diameter of this pulley is D. They ask us to find angular velocity and angular acceleration of this pulley. Okay, let's do it. Let's solve that problem. Solution. Let's start with finding what is velocity of point D. Let's find V star and A star. Okay, in order to do so, let's do our routine for the pulleys. I would like to define this elevation. This will be YB. And also I would like to define this elevation. This will be YD. You can clearly see that our rope that is inextensible consists of two YBs and one YD. Okay, we are at the length level. I would like to differentiate this equation once, just to get to the velocity level, and then I would like to differentiate it one more time. I would like to differentiate it twice, just to reach the acceleration level. Just let's keep in mind that this is constant. So if I differentiate once, I will have 0 that is equal to 2VB plus VD. And if I differentiate it one more time, we will have 0 is equal to 2AB plus AD. Okay. Here we have that VD is equal to minus 2VB and AD is equal to minus 2AB. However, you know that I prefer to solve the problem in magnitudes. So instead of that, let's just write such equations. VD is equal to 2VB and AD is equal to 2AB. I just got rid of the minuses. Great. So that means that actually our V star and A star are equal to, so that means that our V star is equal to 2VB and also our A star is equal to 2AB. Great. We know exactly what is the velocity and acceleration of this end. Oh, excuse me. We know exactly what is the velocity and acceleration of this end of this rope. However, this rope is inextensible, right? This rope is inextensible. That means that velocity and acceleration on each and every point on this rope will be 2VB and 2AB respectively. And in particular, velocity and acceleration of this point will have these values. Let me copy this pulley. I would like to look closer at that pulley. As we said, velocity of this point, let's call it, I don't know, point E, maybe. Let's call this point E. Velocity of this point is also V star. And acceleration of this point is A star as well. Please observe that point C is fixed. And they ask us to find angular velocity of this pulley. So we can write omega of pulley C is equal to v star times this distance. And this distance is exactly L divided by 2. Oh, the other way around. Yes, I made a little typo here. So it should be V star is equal to omega C times L half. We didn't talk about acceleration, but expression for acceleration will be very, very similar. So A star will also be equal to alpha C times L half. These are our unknowns. Let's solve for them. So omega C is equal to 2v star divided by L, and AC is equal to 2a star divided by L, but let's plug in here 2VBs and 2ABs, so it will be actually 4VB divided by L and 4AB divided by L. Plug in values. VB was 5 and L was half. So this will be 40 radians per second. And in here we will have 4 times 0.65. Grab your calculator and obtain that this is exactly 5.2 radians per second. Okay, let's also find omega C vector-wise. So this will be 40k, and it will be rotating this way, I believe. It will be rotating this way. So this is positive value. This is counterclockwise. And AC will be analogical. AC is equal to positive 5.2 radians per second square. I forgot about square here. And this is also rotating counterclockwise. All right, that's the end of example number 2. Now let's do example number 3. Feel free to pause the video and familiarize yourself with the problem statement before we start our solution. All right, so the authors of our manual, they gave us very complicated drawing here. I personally have no idea what is fixed in here and what is moving. I don't know how that mechanism look like. That's why I mean it's hard to figure out it at the first when I look at it for the first time. That's why I prepared a equivalent drawing to what the authors of the manual provided. So we have just one rigid body of this odd shape. This is that body. And we know that our body is fixed at point A. And we know that velocity of point B is v0, equal to quarter of feet per second. And we know this geometry. We know L, we know H, and we know W. They ask us to find velocity of point C. Okay, but before we find velocity of point C, let's find omega of the body. So feel free to pause the video right now and think and try to figure out how would you find omega body. For those of you who figured it out, congratulations. And for those of you who just came here to put their notes together, here's the answer. So I believe that V0 can be expressed as omega body times L. That's why omega body is equal to V0 divided by L. Let's plug in values. This was quarter, if I remember correctly. And I believe that this was 0.9. Okay, grab your calculators and obtain that omega body is approximately 0.2778 radians per second. Okay, this is our magnitude of our omega body. But now let's find its direction. Based on the picture, this picture, we can clearly see that our omega body will be rotating this way. This is our omega body. And this is negative direction. That means that our omega body vector is equal to negative 0.2778 k radians per second. With this information, now we can find what is Vc. We will find Vc based on more general expression for velocity of rigid body. Let us use more general expression. For example, let us express velocity of point C with respect to velocity of point B. So I can write Vc is equal to Vb plus omega body times Rc relative to B. So our Vc will be equal to, I believe that Vb is pointing this way. So our Vb will be equal to V0, 0, 0. We just found omega body. It will be 0, 0 minus 0.2778. And RCB, I will draw in the picture. RCB will be pointing from B to C. This is our RCB. Aha, so it will have V as an x component and minus h as a y component. V minus h 0. Let's figure out this value right now. This will be determinant of I, j, k, 0, 0, minus 0.2778, w minus h 0. And this will be minus 0.2778 h minus 0.2778 w and 0. Okay, so that means that our VC will be equal to V0 minus 0.2778 h and minus 0.2778 w. Great. So our VC is equal to this quantity. Plug in values. $65, I believe. Grab your calculator and obtain that our VC vector is equal to minus 0.29171 and minus 0.73617 feet per second. Okay, this is our answer. And it looks like this is the end of discussion. So thank you for watching this video. I hope you enjoyed it, and see you next time. Bye.